be resistant to the disease. So the way that we wanted to solve this is we took one devil from the northwest, and this was actually honored with the title Tasmanian of the Year, because this animal here was vaccinated with horse blood, and then later with irradiated tumor tissue, and it was immune against the disease for several rounds of injection. And then only recently it died from a very uncontrolled experiment. This one spirit died in the wild, and so we made a devil study group with about 30 animals here and 48 animals in the east. And now you're the experts already yourself. Look at the maternal diversity. What is left? How much genetic diversity? The genetic diversity reflects the ability of the immune system to fight back to a disease. You need, the more diverse your immune system are, the better your chances. This is like playing the lottery with more money, right? And you can see that there is a group of at least 5 animals that have not a single SNP difference in them. This is one before the disease outbreak in 1994. And again, using the museomics, we go back into the museum. Here is my co-worker, Webb Miller, at the Smithsonian. So he's working with me at Penn State, and we work here with a curator at the museum in Washington. And we also have specimens from the London Natural History Museum from 1874. And from this, we could conclude that the genetic diversity of the Tasmanian devil was already low 130 years ago, and that the disease as we see it today is not the reason for the low diversity. It is more that the low diversity is the result that it cannot fight back. And this is really the key point, is the first bottleneck that you go through as a species is not harmful. And a great example for that are the large whales that we almost hunted to extinction. But if you look at those few remaining large whales, they still have an enormous genetic diversity. And again, if we, as the master species that's messing up the environment, would do the right thing, we could completely let this population rebound by stopping to hunt, by not polluting the ocean, by removing the noise from the ocean. But what I'm trying to say, there is no genetic reason why the whale populations should go extinct. Here, this one is a borderline case, and we had to sequence the genome de novo because within 25 million years, there is no sequence reference genome. So we had to create our own reference genome, and that we did by using the 454 sequencer that can sequence up to 750 base pairs. We could nicely assemble the genome and then compare the animals called the SNPs. And so we have made a population structure from the mitochondria, but also from 1 million SNPs that we found between the two individuals that we sequenced. And you can now see how the different groups look. And the other point that I'm trying to make here from that slide is there is one of the reasons we got interested in the project is there's a breeding program underway in Australia, very, very successful. But guess what they did? The entire breeding cohort consisted only of these animals. So you would have lost another 90% of the remaining diversity because they weren't even knowing what they were breeding. And so we got in a big fight because we are saying you need to be an informed breeder and you should not be a random breeder. Know what you breed. This is one of the messages that we're trying to send, and it is next generation sequencing that can provide this data here. This is pretty much no population structure. This is where no Tasmanian devils live in Tasmania. This is the structure we came back by just looking at the mitochondria, and this is the population structure we come back by looking at the nuclear genome. But again, if you don't have the money to sequence a complete nuclear genome, go sequence the mitochondria. So I told you about the breeding program, and it is absolutely clear they can be perfectly bred. They even have breeding programs in mainland Australia where there's no disease. So in principle, by human action, everything can be done. The money is there, the knowledge is there. It's just us whether we do the right thing or not. And in my closing segment of my talk, I want to kind of taunt you with, what about us? How do we fit into the picture? Even what do we know about ourselves? And the goal was to find the most diverse humans on the planet. And because Africa is the cradle of mankind, it was a safe place to look, but it wasn't quite clear where. And so what we tried to do is, from the mitochondrial diversity, it looked like it might be the Bushmen. So we convinced these 4 gentlemen here, who are tribal leaders of their groups, and also Archbishop Tutu, who was the out group in the study, because he is a Bantu, he's not a Bushman, or at least we thought he was not a Bushman, and then compared it to the genomes of these 4 men. And most of our studies were done in Namibia, so down here is South Africa, and we had 3 groups over here and 1 group here. One very interesting concept that I'm always find interesting to mention, even so I'm not entirely sure that this is true. One of the big differences is that the Bushmen are hunter-gatherers, so they are not herders and they don't do agriculture. And I kind of think that this culturally is related with having round housing. In the moment in Africa you find somebody building square houses with right angles, then they do agriculture. And I don't know if somebody here would know whether this would hold up here in India, if there would be any kind of hunter-gatherer populations that would live in square houses or in round houses. In any case, you can see that they have a very different phenotypes with them. They look at me and feel I would make a very poor hunter. This is what they told me. Too big, too slow, always sunburned. And so this is the sex-specific roles. Men go hunt, and this is Vanessa Hayes, my co-lead on the project, and she's with the women gathering from the bushes. And so one of the interests in this project was also to learn, could we find genetic differences also in the physiology of a human that would be correlated with a different type. And again, we look at the mitochondria here. And in principle, if you envision the human tree has only 2 branches. The one branch, the human tree has 38 groups, and 36 of the groups are on one branch, and only 2 of the groups are on the other branch. And this is the LO branch here, and the only people that are in this LO branch are the Bushmen and the Pygmies from Central Africa. All the other Africans and only 2 groups for the non-Africans. So all of us here are either M and N groups. They would be in L, L2, L3. And to get back to our story is all the Bushmen that we looked at, they were supposed to be in this group, and you can see that's the case. And Archbishop Tutu, ABT, was supposed to be in this group. And he was not. And this immediately told us that Archbishop Tutu is not a pure Bantu. He's not having a Yoruban history. And in this process of his ancestors migrating down in the Bantu expansion from West Central Africa all the way to southern India, it is he had an ancestor. There was a female Bushman in his lineage. And what you see here are 20 random Europeans for the mitochondria. And you yourself can look at what you think that the European diversity is. It's pretty much like a mammoth. But this is at the same time, all of those people are living at the same time. So you would have 20 to 25 differences in the European population. And if you now compare this with the Bushmen and look at Archbishop Tutu, he has a whopping 100 differences compared to the European Cambridge reference. 5 times the diversity that 2 Europeans would have with one another. But what is even more stunning is the fact that if you remove the Cambridge reference sequence and you use one of the Bushmen, KB1, as the reference, then the Bushmen still have 85 differences pairwise between one another. So you have people that live in walking distance to one another. They cannot speak the same language. It's almost like here in India, right? With how many languages? 22? many